In this video, I'm walking you through the test bench for the dabble 14-bit test bench. Okay, in this particular case, I'm making this test bench to be self-checking. By that I mean, it's going to not only run your code and get the answers coming out, it's also going to check that with expectations. Okay, so before, many of our test benches, you had to go into the screen and look at, run this in Vivado, look at the waveform screen, and then individually check different conditions to make sure that the circuit was operating the way you wanted to. But in this case, we're going to make it self-checking, where you don't have to manually intervene and take a look at what happens on the screenshots. It's just going to go through all the test cases and notify you if there's errors. Okay, you can see where that'd be an advantage if you're developing lots of code and you might have a change to something in your code base. If you have a lot of self-checking test benches built into the process, that makes changing code a lot easier because you can rely on these self-checking test benches to make sure nothing is broken and move forward with any revisions you might have. Okay, so in this case, we're going to set this up. Remember, we haven't done a lot of test benches, but remember the format. The first thing you do is you give it a module name, and so this is the descriptive module name that we're going to use. And what you notice is there's no ports, right? There's no open bracket, and then we start to write wires and stuff. It's just a semicolon at that point, and then for inputs, what do we use? Inputs, we use regs, okay? In this particular case, we know we're going to have a binary input that's 14 bits, so that makes sense to do it like that. All right, and then with a test bench, all the outputs should be wires, and so we have the ones place, we have the tens place, the hundreds place, and the thousands place. Those are the outputs coming from the 14-bit dabble algorithm that you implemented in Verilog. Okay, so the next thing you do, all right, so let me clear all this. All right, the next thing you do is you need to instantiate. So we need to instantiate the test bench instantiate the hardware that we're trying to test. Okay, so we're trying to test this dabble 14-bit algorithm that you modified. Okay, remember you modified the 8-bit to turn it into 14 bits. Okay, so that means you need to instantiate, and the way we have this set up, it's really easy to instantiate because binary just gets connected to binary, BCD1s gets connected to BCD1s, and so forth. You've seen this kind of thing before. Okay, so at that point, we've done step 2. Step 1 was we determine the regs and the wires. Step 2, we instantiate the item that we want to test. Now it's a matter of writing code that will implement the functionality that we want within the test bench. All right, so here's where things get interesting to me with test benches. You have programming constructs that look very similar to what you might see in MATLAB or C, so that you can actually do things in a little more flexible way so that you can check to see if your circuits are working. Remember, test benches aren't synthesized into hardware, so you have a lot more flexibility with the coding aspect of that. And in fact, you can make test benches that are completely written in C, for example. But we're going to use this approach where we're using some Verilog kind of constructs mixed with some programming constructs. Okay, so my point is, you start to write code, and what we're going to want to do is exhaustively check, does this work for every input combination that would result in a valid display? Okay, so we only have 4 digits that we're displaying, so doesn't it make sense that we can go from 0 to 9,999? We can't go any bigger because we don't have enough digits to display any more than that. So we're going to exhaustively check that. 10,000 cases is not that many, so we can get the computer to run that for us. Okay, so the first step we have is we've assigned binary to be the 14-bit representation of the word of n. Okay, so by default, when you make a reg, Verilog is going to cast the value of n. You're telling it n is an integer. We're going to take 14 bits and assign that to binary. Okay, so at this point, we have the binary value of n. Okay, so remember n starts at 0 and it ends at 9,999, and then we increment along the way. So we take the first binary value, and now at this point we check what should we actually get. Okay, and so I'm looking at the output of my BCD, binary to BCD converter. I should get the thousands place. Okay, so that's a bit pattern for thousands. If I multiply that by 1,000, I get the thousands place. And then I form the hundreds place in a similar way, then the tens place, and then the ones place. So I'm building up what the circuit actually gives me. Okay, so that's why it's called actual. All right. So from there, we can make it self-testing because we compare actual to the value that we started with. Remember, we started with n. That's in decimal. That got converted to binary in this step. All right, and then we check. Does the actual decimal number give me what I expected? All right, and if it doesn't, there's some display logic that gets shown, and we can count the number of errors. Okay, so from there, you have to decide what makes this circuit work. Well, if the errors are 0, it passes. If there's any error at all, it doesn't, it fails and should display that you have an error. Okay, so that's how a self-checking test bench would go. When you run this, you should be able to look at it and tell whether it passes or not.